Swayam Prabha. Digital India. Educated India.
I've been doing this for probably the last 12 years, okay, and and I consider this as extremely important because you see, you guys are going to be the torch bearers of the nation. I mean, the whole faith of the country depends on you, your contributions, okay. So, as you know, one of the aims of the RSIC is that, you know, that people should appreciate and see importance and have enthusiasm in doing science, okay. So everybody knows that, you know, the way things are polarized now, either you get into engineering or medicine, okay, but it's not, they are not the only avenues. In fact, I mean, this trying to get into engineering or medicine, you know, it is like a rat race, and you know, but the point is that you see, at the base of everything, whether it's engineering or medicine or whatever it is, even if you go into, you know, things like economics, you go into banking, okay, you go into anything, actuarial science, okay, even humanities. So you see, nowadays the usage of you know, mathematics, for example, is fundamental to everything, okay. Even if you are doing a psychological study, finally you have to measure something, and then you have to kind of interpret the data, okay, and then statistics and probability comes in, okay, is required, okay. So mathematics is the language that you have to learn. So that's one of the fundamental sciences that is very, very important. So you see, we are producing too many engineers and doctors, okay, and not that it's a waste. I mean, people go to other countries and they find avenues, but the point is more important than that is that I don't want to say that, you know, don't run after this rat race of joining IIT or something like that, and you know, just try to end up being an engineer and doctor. I'm not saying don't do that. I'm saying apart from that, there's a much more serious problem. The serious problem is that we are low on basic sciences, okay. See, we are low on basic sciences, and of course I've already told you, mathematics is a basic science. It's it's indispensable. You do anything, at the end of it, it's math, and you need to compute things, okay. And then what about the others, physics and chemistry and biology, okay, they are all important. I mean, they are all equally important. You get into anything, you know, these things will come in, okay. And so we are kind of I think the whole philosophy of RSIC was that, you know, we want to tell school kids that, you know, after you finish your school, it's not that only engineering or medicine is the only, you know, way out. There are so many other things. There is research in basic sciences. It's extremely important, okay, and it is very, very fundamental, okay. And you cannot, without strong foundation in basic sciences, you cannot do anything else, okay. No matter you know, whatever you're doing, suppose it's some, you know, you have some application in instrumentation in biology or medicine, okay, everything involves engineering, it involves physics, and you know, for example, when it comes to, you know, understanding biological systems biochemically, then chemistry comes in, okay. So there are so many things. It's very I mean, if you look at it, it's very, very clear that the countries who have basic science you know, research, who spend a lot of money on basic science research, they are the guys who seem to have all the technologies, indigenous technologies, okay, and therefore they are completely self-sufficient, whereas we have to import things, okay. So therefore, moral of the story is basic science is very, very important. That should be a mainstay. That should be one of the attractors, not just like a rat race going behind engineering or medicine, okay. So that is the philosophy of the RSIC, and I have been involved in this right from the first year it started, I think. We work in geometry, okay. Geometry ranges from very simple things like circles and triangles that you see in ordinary geometry, up to, you know, the geometry that involves more advanced things like, you know, manifold theory and string theory, particle physics, relativity, also, you know, structure of subatomic particles and things like that, okay. So there's a whole you know, spectra of things that come under geometry, okay. What I am going to do in this two lectures is try to tell you something about differential geometry, okay, and it is also going to be a kind of let me say something to whet your appetite, okay, at least for the people who want to do a project under this, okay. So I want to talk about differential geometry of curves and surfaces, okay, and so this is the so let me write here. So at any point if there is something that you don't understand or you want to ask a question about, just please raise your hand and then please feel free to talk to me, okay. So it is a lecture, but still it is more like it's like a conversation at points when it needs to be, okay. So 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 I want to tell you the idea of differential geometry, okay, and in general the most important focus of differential geometry is what is called as curvature, okay. So this is the most important keyword, all right. Now see I would like to first give some instances, some questions, some interesting things that will appeal geometrically, and then I would like to tell you that these things, if you want to really believe in these things, which you will intuitively at least believe, but then the idea about math is that you must give proofs, okay, and without a proof nothing is kind of certain, okay. So this is the problem with mathematics. So things which are obvious, okay, they are not obvious to mathematicians, okay, or a mathematician will not accept it unless you give a proof, and this is there are many things. So of course my favorite thing that I allude to is things in number theory. For example, you see, it's known that for example I mean for 300 years or 400 years, so there are very simple questions which for which you can believe it, but there is no proof, okay. And so for example there is this so called Goldbach conjecture, which is about I think 300-400 years old. So it is every even number greater than 2 can be written as sum of 2 primes, okay. So if I take something like 8, it is 5 plus 3, okay. If you take 17, it is, I mean if you take 14, then it is 7 plus 7 if you want, okay. The 2 primes can be the same, okay. Now this is called Goldbach's conjecture. The point is it's still not proved, okay. So what is people have used computers to test large numbers, even numbers, and try to break them into 2 primes, and they have succeeded, they have never failed, okay, but that is not a proof. What is a general proof? A general proof in mathematics will say start with an even number. That means you have to take the number as 2 times n, where n is a natural number, positive integer, okay. That's how every even number looks. You have to start with this 2 times n, and then you have to produce 2 primes p1 and p2, okay. That is, you have to show that there exists 2 primes p1 and p2, so that p1 plus p2 is 2n. So this is the mathematical statement. Given any positive integer n, primes p1 and p2, which will naturally of course depend on n, and they need not be unique also, but there exists at least 2 such primes p1 and p2 which depend on n, such that p1 plus p2 is 2n. This is the statement, okay, if you make it mathematically. Now this statement is not proved, and if any of you tries to prove it, you will get probably a Fields Medal, which is the equivalent of the Nobel Prize in mathematics, okay. So you can see the depth of the problem. Mathematics abounds with such things which are very simple to state, which are extremely hard to prove or not prove, okay. So what as mathematicians that we do is that we want proofs, we want to know for sure that something is true, okay, and so that is where the crux of mathematics comes. You must have a statement that you want to prove, and of course the statement is always motivated by some geometric things, or it is motivated by some study. For example, people realize that you take any even number, you are able to break it into 2 primes. Now you keep doing that forever, and whatever case you test, you are able to do it. So then this becomes a question, okay. So that's why I am saying this is that the mathematician's point of view is not to believe until and unless you have a proof, okay. And the proof is what is the structure of you you have some basic assumptions which are called axioms, and from the axioms you start making deductions. You combine the axioms, and what are you trying to prove? You are trying to prove a statement as hypothesis and conclusions. Okay, hypothesis is what you assume, that is certain conditions, and then the conclusion is that you are going to get this. All right, now the idea is that once you make all these assumptions, the hypothesis, what you are supposed to do, what a proof is supposed to do, is to take the logical basis of the theory, which are the axioms. You mix these conditions that are given to you with the axioms to get better conditions, and which come closer and closer to what you are trying to prove. And finally, if you hit it, then you have proved it. Okay, so this is the logical framework. Okay, so and here again there are certain problems which are again very, very deep. For example, if you take something like very naive and very, very fundamental like set theory, even in set theory, there are statements which are mind-bogglingly strange. So there is one, let me tell you about one such statement. This is what is called as the axiom of choice. Okay, so this axiom of choice, what does it say? It says a very, very simple thing. It says something like this: suppose you go into a hall where you are a sweet shop, okay, and you have lots of boxes of sweets, okay, each one having a different type of sweet, say laddus and jangris and jalebis and so on. Okay, now if I ask you a box with one laddu, one jangri, one jalebi, okay, that means it's a very simple thing and you will be able to do it. Okay, now assume that I give you a very general version of this. I have a huge collection of non-empty sets. These are each set represents a type of sweet, okay, box, okay, and they are non-empty. That means there is at least one sweet available. And then I ask you to form a new set such that you put one element from each of these sets into this new set. Okay, now this is so obvious. Okay, this is called the axiom of choice. Given a collection of non-empty sets, I can form a new set such that it contains exactly one element from each set in the collection. Okay, this is what is called as axiom of choice. And here is the amazing thing. Why is it called an axiom? Isn't it obvious? So here is the mathematics. If you remove this statement from set theory, then using the other axioms of set theory, okay, which involve, for example, existence of union, intersection, okay, containment and things like that, normal rules of set theory. If you remove this axiom of choice, then from the remaining axioms you can neither prove this nor disprove it. Okay, that is the extent to which it is so deep. All right, so there are certain things which you remove from the rest of the axioms, you can neither prove it nor disprove it. So you see, it's like undecidable. Okay, this is some kind of incompleteness. So what is mind-boggling is that such an obvious statement. Okay, if anybody tells you that I have a collection of non-empty sets, and then I have to just form a new set by picking one element from each set in this collection, you will say, of course, that's obvious. So why can't I do it, right? But the point is, you have to assume it. You have to assume it is true. If you don't assume it's true, you are in trouble. You can neither prove it is true nor can you prove it's false. Okay, so this is what is an axiom. See, an axiom is like faith, like you have faith in God. Right? It's like you don't say, I will not believe a God whom I cannot see. But where is the God? There is no God that you can see. So it's a matter of faith. So it's like that. It's a basic assumption. If you remove it, you will be in trouble. So this is one. So mathematics. So what you must understand is what you start with as the axioms. They are so fundamental. If you remove one of them, it can be a big mess. I'll give you one more axiom, which again you will say that this should be obvious, but it's not. Okay, and what is that? That is the so-called Playfair axiom, Euclid's parallel postulate. If you have heard about it, it's a very, very simple statement. Take a plane, draw a line on the plane, take a point with the line. Then there is one and only one line through that point which is parallel to the given line. Many of you know analytic geometry. You will immediately write the equation of the line as ax plus by plus c equal to 0. Okay, and then you want and you have a point x naught comma y naught which does not lie on the line. That means ax naught plus by naught plus c is not equal to 0. Then what you will do is that, how will you get the parallel line through x naught y naught? You will just take the parallel line as ax plus by plus d equal to 0 and substitute x naught y naught in that to get the value of d and put it back. right? This is what you will do. So that means you have proved this, but here is the amazing thing, your proof is flawed, because you have already assumed in the proof, without your knowledge, you have already assumed. So the point is, in Euclidean geometry, if you remove Euclid's parallel postulate, neither prove it nor disprove it. Okay, this is so it's an example of a kind of incompleteness. So what you must understand is that axioms are like fundamentals. They are like God. If you remove them out, then you are in trouble. You cannot proceed. Okay, yeah, you have a question. Please.
For the Euclid's parallel axiom, can't we say that for a line to be parallel to another line, it should have the same slope, and there's only one and only line which has that slope for a particular point passing through?
That's right. That's equivalent to that.
No,
that is equivalent. That is a kind of an equivalent version. That is through a point. For a given slope, there is only one line passing through that. That is an equivalent version. Okay.
So this is you're saying this is the same statement as the axiom.
Yes, but you see, so the point is, when you say two statements are the same, it's slightly more involved than that. What you have to do is that when you say two statements are the same, here the set of axioms and there the set of axioms have changed. Okay, so you have the usual set of axioms where Euclid's parallel postulate is there. Then what you do is that you remove from one of them, you remove that and put whatever definition you want to put. Then you have to do a logical deduction to show that these two systems are equivalent. So there is it all sounds very, very easy, and almost nobody will ever doubt it. But the point is, when you start writing down a logical equivalence, that's where you get into trouble. See, the problem is that logical equivalence cannot work unless you apply all the axioms. Okay, and when you don't have an axiom, you have to get around it by either deriving the axioms from the other axioms, or in connection with whatever is given to you. That's where the problem is. See, it's very, very subtle. You can't see it. It's like how else can it's like, it's obvious that if I have a line and you give me a point, there is only one line to it parallel to that. See, this looks geometrically obvious. Nobody will even question it. You see. Similarly, if I tell you that if I give you a collection of non-empty sets, I can find a new set which contains exactly one element from each set in the collection. That's so obvious. Nobody will ever argue about it. The point is that what is obvious, you must be always beware in mathematics. What is obvious? If it is an axiom, then it is something that you cannot fool around with. If you remove it, you will be in trouble. Okay, so mathematics this is the kind of things that mathematicians are involved. So what is a proof? So why I am saying this is why axioms are so important. Mathematicians, as far as mathematics is concerned, you want proofs, and to give a proof, you need axioms, and axioms you better not meddle with. Okay, if something is not available at the axiom level, then you are in trouble. So I am saying, don't take axioms lightly. They are like faith. Okay, no, that's the problem. That's the problem. See, if I cannot disprove something, okay, then there is no guarantee. See, for example, the Goldbach conjecture, people have not been able to disprove it by large calculations. But does that mean that it's true? Does it mean it's false? Maybe there's some huge even number, say 10 to the zillion digits, even number for which it breaks down. Okay, how do you know? Unless you have a general proof. See, this is a problem. See, we live in under many assumptions. For example, we assume that all logical systems, you give me any question, it has an answer yes or no. It's either yes or no, right? That's how we live. But it's not like that in logic. You may have an undecidable question, okay, for which you can neither say it is yes or no. In fact, you may think that this is very rare. It was Gödel who proved that it is not rare at all. In fact, he gave a theorem which scared everybody. The theorem says that give me any system, there is always one undecidable question. There is always one question. In fact, there is always something that is inconsistent with the system, in the sense that you cannot say yes or no. There is a question for which you can neither say the answer is yes or no. There is always one such thing. It's called incompleteness. Okay, so this is a problem with foundations. Okay, so what I am trying to tell you is this is what is called as this is at the very base of set theory. Okay, so I mean, so I am saying that don't take, the techniques of mathematics, don't take them for granted. Axioms are very, very important. Don't, axioms are like God, okay. Then from the axioms given, whatever is given to you, you build up you build up proof. And getting that proof is the, that is the holy grail, okay, for mathematicians, all right. And until I have a proof of something, I don't believe it. That's the way it goes, okay. Anyway, so this is just this is just to tell you why mathematics is important, all right. Yes.
Sir, how do we prove that two statements are equivalent?
No, of course, that is a so this is again, this is part of logic, okay. You have to start with the statement, then you have to take the axioms, you have to combine them to finally get the other statement. You start with the statement as being true, then you have a bunch of axioms which are always true, then you mix them together, and then you make some observations, calculations, reductions, then finally you get that the final statement that you want is true. So that is the logical structure. But then this finding a proof is this middle part which is like a black hole. That is, you have to mix what is given to you with the axioms, and you use your head and intelligence and creativity, and then cook up something that leads you to truth of the final conclusion, okay. So that's what proof is all about. So you see, it is a big job. What are the axioms to start with? They are very, very fundamental. You can't fool around with them. Then at the end of it, you have to get a proof. If you don't get a proof, then it's of no use, okay. The problem is still unsolved. For example, twin prime, this Goldbach conjecture. Then the other thing that I always almost say is the twin prime conjecture, which is that, that what are twin primes? They are closest primes. Like, if you want 3 and 5, okay, 11 and 13, two closest primes can be at a distance of 2, right? It cannot be 1. They can't be next to next, because one of them will be even and then it's not a prime. So the minimum distance between two primes can be 2. But if you start writing the prime numbers, you will see that they are all, going farther, they are going farther and farther away, okay. So if you go down the list of primes, they should get very, very sparse, okay. They should be very, very far away, and therefore you should expect that if you go far enough, then you should not get primes which are very close. But the twin prime conjecture says you can do it, no matter how far you go down the list of integers, okay, zillions and zillions. You go how far, no matter how far you go, there are always two primes of the form p plus 2. That is a twin prime conjecture, okay, and it's not proved, all right. So there are many such things, and anybody who proves it is is a hero, okay. So there are many things like this in number theory which are about which we don't know anything, okay. So therefore, so let me get back. So this is just to tell you why, what occupies mathematicians and why they are a crazy lot, okay. Like you find most of them looking somewhere into the heavens or in their own thoughts and thinking about something, but this is what they are thinking about. They are worried about why something is true and how to deduce it, okay. So this is the occupation of mathematicians, all right. And of course, it's not just a philosophical thing. When it comes down to real life, this is also the occupation that you need to get formulas. Why do you need formulas? Is because you want to compute. And why do you want to compute? For example, is you want to compute things because you need it, okay. So if I have a blood pressure monitoring system, instantaneously I would like to calculate the blood pressure. I would like to calculate the heart, the pulse rate, okay, and so on and so forth, which is what, these little things, what are they called? What is that? Oximeters, for example. How do they work? It's all, it's a mix of engineering and technology and finally math. There is a chip that has been hardwired with a mathematical formula which immediately outputs the values that you want, okay. So it's all fused together, all right. So the point is that you have to compute. So let me tell you first of all, let me tell you some interesting things about differential geometry, okay. Yes.
How do we know whether the set of axioms which you have chosen are the most optimal set of axioms that
we don't. Yeah, these are all questions. Can you find a minimal set of axioms which imply all the other axioms? These are all very difficult questions. Normally what we do is that we take a set of axioms that are comfortable enough and give all the proofs that we want, and then we don't worry about it. But then the point is that there is a whole branch of what is called as logical set theory and logic, in fact, where people really start worrying about these kinds of things, and they try to fix up certain questions like the one that you asked. So that leads into what is called as logic. Okay. So it's not clear. It's not clear. Basically, what we do is that usually for all practical purposes, you assume a set of axioms which are good enough to give most of the proofs. It is called the Zermelo-Fraenkel set theory with the axiom of choice. It's called as ZFC. Okay, and that is the usual set of axioms that you use, and that is good enough for everything. Okay, but the problem I want to tell you is that remember that proof involves starting with a set of axioms and then getting to something. Okay, so the axioms are very, very important. You cannot fool around with them. Okay, so let me get to curvature. So you see, so I will begin with the study of differential geometry has been there over more than I should say 1000 years, 1500 years, right from the time when people were measuring the positions of the planets, the celestial objects. Okay, and right down to modern treatments that started around the 15th 16th century. Okay, and finally which were all kind of brought to very nice mathematical structure by Carl Friedrich Gauss and Riemann, okay, and Hilbert. Okay, so this is a very, very deep area. So I will tell you certain interesting things. So the first thing is what is called as a cartography. So cartography is what it is the it is the art of drawing maps. Okay, so this is a study of maps, and you need, of course, you need maps to navigate, to find your way around. Okay, so the question is, so you have a so here is the situation. You have the Earth, and you have, let us say, a country like India here, and then you want a map of India on a piece of paper. Okay, and of course you use this kind of map to do. Okay, my picture is not very good, so with due respect, my picture is not to scale, but I am drawing something like this. Okay, there are better pictures available. Okay, so you want to draw a map, and so what is the question? The question is, I want an accurate map. So the question is, can you draw an accurate map? So what is this accurate? What does accurate mean? See, accurate means that what does accurate mean? First of all, you see, if I give you two places, like some place, so let me draw some, let me draw Chennai and let me draw Delhi somewhere here. Okay, so for example, I would like to know what is the distance between these two places. Okay, and so I want distances to be correctly measured. So basically, what does it mean? It means that if I draw this length, if I measure this length L, which is a straight line segment on my map, and this, so this is Chennai and this is Delhi. Okay, then distance from Chennai to Delhi will be L times some multiplication factor. Okay, that is the scale of the map. So mu is the scale of the map. So usually you will find something like this, saying that this is 0 to, let us say, 1000 kilometer. Okay, something like this you will find. Okay, in every map has a scale. Okay, so that if you measure distances on the map, multiplying by the scale will tell you how much is the distance. Okay, now the point is that when you say accurate map, what you would like to have is that you want that it shows distance accurately. Okay, you want that. Then the other thing that you would like to have is that, for example, if I have two different places, okay, then I would like to have the the angle between the two the two directions. So Chennai to Delhi is here, let's say Mumbai is here. Okay, so then I have this. So wait a minute, let me draw it correctly. So there is this, and then there is this angle. Okay, and of course this angle is kind of if you want this kind of angle should be, for example, if you want a direct line of sight in the in that direction. Okay. So you would like a map to give you angles correctly. Okay. And even inside a city, for example, I would like, for example, if I am positioning some communication equipment, for example some microwave or something like that, which needs to go in a straight path, then I would need to know how to align the towers so that it goes in a straight path, and therefore I need to know angles correctly. So the accurate map should also show angles properly. Okay, angles between say 3 points. Basically, if you give me 3 points, I get a triangle. I need to know all the angles of the triangle. Okay, an accurate map should do that. Then the third thing that an accurate map should do is that if you zoom into a portion of the map, say something like this, if I zoom in, then if you give me if you zoom a portion of the map, okay, then I would like to measure the area of some region. So suppose this is let us say suppose this is IIT Madras. Okay, so this is in the map you have various divisions. Then this IIT Madras, I would like to know what is the area. What is the area of a region in a map? So what is the area? Okay, so a good map should also show areas correctly. Okay, so you see a perfect map should show areas, it should show distances, it should show angles correctly. Okay, and the question is, can you draw a perfect map? So yes.
Won't it be impossible to draw a perfect map, because when we are assuming a sphere, well, we know that some of the angles in a triangle is not necessarily going to be 180 on the surface of a sphere, whereas here when it's a rectangle, when we're drawing the angle, we are assuming that some of the angles of a triangle is 180. So it shouldn't be possible to draw, well, at least the angle part of it perfectly.
Yeah. So that is, so this is what is expected, but the question is that so there are so you can question that the what you are drawing is a portion of the sphere which is curved, but you are trying to flatten it, and when you flatten it, something is going to go wrong. Okay, so and that is correct. But the point is, I would like to ask that if you zoom in and zoom in and zoom in, for example, suppose I zoom into a region such as IIT Madras, which is kind of just smaller than a point on the scale of the earth. At least in that case, can you still draw an accurate map? Okay, so you zoom into, let us say, let me take something like very small radius, half kilometer if you want, which is very, very small, or let's say even 100 meters. Let's say even 100 meters. Okay, can you draw a map? Okay, so of course there are two answers to this. One is, if you are not worried too much about accuracy, the answer is yes. As you make the area smaller, that's because the error is going to become very small. But the actual answer, if you want a perfect mathematical answer, okay, so mathematical answer means you really worry about the error, no matter how small it is. Okay, see, this is another attitude of mathematicians you have to get used to. Okay, so if I am going to draw, if I am an engineer and I want to cut out a circular disc, okay, then if I know its diameter, I know that the circumference is pi times diameter. Okay, and the value of pi that I will use is, well, will you use 22/7 or will you use 3.141 blah blah blah? Okay, how much blah blahs are you going to use? Okay, so for all practical purposes, if it is let us say a tiffin plate, okay, I really don't care about error beyond, let us say, half a centimeter or something like that. I really don't care. So I can use an approximation. But a mathematician will worry about it, okay, till the last digit. Okay, so that's so in fact the answer is that you can never. So the answer is actually a big no. Okay, you can never do it, even if I want to draw. Suppose I take the palm of my hand, okay, just this much area for this portion of the surface of the earth. Okay, right, if I want to draw an accurate map on a plane, I cannot. Okay, I simply cannot. There will be an error. Maybe the error is very small, but it will be. You can never get equality. Okay, and so it is kind of obvious in a way, as he says, because the sphere is curved on the one hand, and you are drawing something that's on a sphere, and you are trying to represent it on a plane which is not curved at all. So you see, the reason why this is not possible, okay, is because of the curvature of the sphere, okay. And the easy way to say it is the following. See, suppose suppose this the sphere, the surface of a sphere was like a peel of an onion, and I drew a map, okay. If what I am trying to do is I am trying to take that, I am trying to peel that out and flatten it onto a surface of a plane. But when you flatten it, you can't flatten it without involving some creases. See, this is basically the same thing as you take a football, okay, and you cannot take a plain piece of paper and wrap it on the football without making any creases. You cannot uniformly do that. Whereas, you see, I can do, it's not true, if you take a cylinder, okay, I can take a piece of a cylinder and put it on a plane, okay. I can take a piece of plane and put it on a cylinder, I can do that accurately, okay, but I cannot do it with a sphere, okay. And why are all these things happening? For example, I can take a piece of a plane and roll it on a cone without any creases, and I can take a cone, cut it along any generator and flatten it to a plane. I can do that. I can do it with a cone, which is a curved surface. I can do it with a cylinder, but I cannot do it with a sphere, okay. So what is going on? So the real answer to this is what is called as it's a very deep theorem. It's called Gauss theorema egregium. It's called Gauss's remarkable theorem. So it's called Gauss theorema egregium, which says that you cannot do it, okay. And how do you prove such a theorem? You have to use differential geometry to prove it, okay. So I am trying to tell you several things which will give you the appetite as to why you should do differential geometry. I mean, some practical things. So Gauss theorem egregium says that you can never do this, okay. And in fact, so the question is, let's come back to ground zero. Well, if I can't do something, that is in the end of the story. I have to do something, okay. If I can't do it accurately, at least I should do it with some error. So what is it that you can do accurately, okay? Of course, if you are allowing errors, anything can be done, okay. See, all these maps that you see in your Google or whatever it is, or if you look at maps on a map book, okay, they are all accurate up to some error, okay. And of course, because of GPS, the Google map can be made terribly accurate, okay. And that's because it takes the GPS system will take care of the the curvature, okay. And that is the kind of thing that is required for satellite navigation and missile tracking and things like that, okay. But the point is, what is it that you can accurately do mathematically? So here is what you can do mathematically. You can create a map which shows angles correctly, but it will distort areas. You can create a map that shows areas correctly, but it will distort angles. In any case, every map will distort distances. So this is what you can do, and this is again mathematically you can prove it, okay. So what is possible? So let me write what is possible. What is possible is can get a map that shows distances. So let me write, so I will put angles, areas, angles, distances. It shows areas correctly, but it distorts angles and distances. It shows angles correctly, but it will distort areas and it will distort distances. In all cases, the distances will always be distorted, and you must more or less realize that if you can find a map that does not distort distances, then it will also not distort angles and areas, okay. The point is that this can never be adjusted. You can never measure distances accurately. You cannot do it, okay. That's because of the curvature of the sphere, okay. What you can do is a map that gives areas correctly, or you can get a map that gives angles correctly, okay. And so the maps that give area correctly such maps are required for things like if I want to know what is how to compare the area of the United States to the area of India, for example, from a map, then you need a what is called an equiareal distribution map, okay. And these kind of maps are used also like pie charts to show how much of something is concentrated in certain area, all right. So that is a pictorial representation, okay. By the way, if you look at a map, you can go and search on the internet, look at an equiareal map of the earth, you will be surprised to see that the sizes are all very different from what you saw in the usual map, okay. Then the other thing is you can have the angles correctly, okay, and that getting the angles correctly is important for example aircraft movement and navigation, because you need to know in which direction which city is there, okay. And of course, at least in an aircraft I can change trajectory and get back, but if it is a missile or something that's being fired, I cannot easily change trajectory, okay, because that will be a strain on fuel again. And if it is a satellite that's going in an orbit, then it has to be in a precise orbit, okay, you cannot simply change it, okay. So I need angles correct, okay. So these kind of things are, so mathematics says that you can really do it. I can get a map which is accurate in angles, or I can get a map which is accurate in areas, but not both, which is therefore I can never get a map which is accurate in distances. And a map that is accurate in distances will also be accurate in areas and angles, okay. So that is a matter of geometry, okay. So yes, you have a question.
Yes, sir. So you said that any flat map there will always be this error.
Yes.
What about, for example, Google Earth? They have projected everything onto the scale. They've kept the spherical shape, but as you zoom in, it becomes flatter and flatter and flatter. So that will not have any errors, right, sir? Because it's still
So that's what I am saying. If you use GPS, it can be made errorless. If you are using GPS, it can be made errorless, because now it is what you are seeing is actually zooming in of a map on a sphere. Actually, Google Maps or any GPS system actually computes maps on a sphere and flattens it out for your need. As you change the zoom factor, it will make the corrections required. The map that you see will be appropriately adjusted. And for military applications, it is designed in such a way that you can make angles the same, you can make the areas the same, because they need all that information. But for general public, it's still kind of quite accurate, because Google does what you see is only a projection, and it's already accounted for the error, okay. So that's right. But the point is, the original point was that you must imagine that this is in the middle of the 15th century or 16th century, when nothing was available, okay. But then Gauss was smart enough to say that no, it's not possible, you don't even dream about it, okay. You can only get approximations. But the point is that this again in math, what is really important is, if you say something is accurately possible, you have to prove it, otherwise we don't believe it. If you say it's not possible, also you have to prove it, otherwise I am not going to believe it. You disprove it or you prove it, both of them are equally important, okay. And that was a fundamental thing that Gauss did, okay. So what I want to tell you is that the proof of this is involves differential geometry, okay. Basically it's trying to understand how surfaces are curved. How do you study the curvedness of a surface, okay. Yeah.
Sir, so let's take a rectangular map. So when we see, it's like let's assume like it's a rectangular map and the area is correct in that. So the angles might not be wrong, but the distances must be correct too, no sir?
No, it will get distorted. I mean, the areas are distorted in a nice way, so that you make up for the curvature, but then when you distort it, it will necessarily distort the angles. No, that is the statement. See, the statement is that if you try to make the areas accurate and distort the map, okay, then your angles will become inaccurate. If you try to make angles accurate, then the areas will become inaccurate. It is something like your uncertainty principle. Delta x, delta p is always greater than or equal to h by 2 pi, right? So you cannot get both accurately, okay. It's something like that, okay. You cannot really do it is the theorem, okay. That is the theorem. And you must understand that the way this is proved is, if you can do both, that means if you can adjust areas and angles accurately, then you should be able to adjust distances accurately. That means you get a pakka accurate map, and that is not possible. That is not possible is the theorem, okay. So it is kind of it's involved. It's not. It involves study of curvature of surfaces, okay. So it's a deep theorem, all right. So mathematicians are, see, the point is why mathematics is so important is when mathematicians say something is true, I mean you take it for granted. I mean if applications take it for granted. For example, I am shooting a missile at, in a certain direction. I need to know accurately this is the correct direction. You believe the mathematics. Okay, if when you are moving in a plane, regardless of, probably you are not even aware that at every point the speed of the plane, the drag on the wings, and then the lift on the wings, everything is being monitored and everything is being kind of kept so that you don't know what's happening. But any change in any of these parameters can be disastrous. Everything has to be computed properly and it should be in real time. It has to be updated, otherwise you are in a lot of trouble. Okay, so there's a lot of technology that's being used and it all involves mathematics and computation. And why should you believe the computation? Because there are formulas. What are the formulas? Formulas are basically the theorems which people have proved, and it's because they are theorems that people believe in. Otherwise, why should I believe in something? Okay, so it's a question of belief, and belief comes only by proof. Okay, you see, that's where the math comes in. Okay, that's what math is all about. Okay, so of course there is a softer part of the math where you guess something is correct. Like for example, you realize that on a sphere things are going to be distorted, so you cannot flatten it out. To guess this is intuition, is a geometric intuition. But the point is in mathematics is it begins from there and then finally it has to condense down to a paka proof where you write down everything and show that this is not possible or this is possible. Okay, that's what math is all about. Okay, so let me
So these proofs involve action.
Pardon?
These proofs.
Yeah, these proofs involve, for example, at the simplest level, they will involve. It's called differential geometry because it will involve calculus, and it will involve differential and integral calculus, and it will involve standard analytic geometry, and continuity and things like that. So these proofs will involve the standard mechanism of calculus. And for the mechanism of calculus, there is going to be a base of geometry, axioms of geometry. So they are going to be there. I mean, something like that has yet to happen. So one of the things that people are fearing now is quantum computing, where you have a quantum computer which can break all standard non-quantum crypto systems, and then this is so that's why there is a race for quantum computing. Okay, so then the problem is that the way it behaves is something that we don't know anything about. Okay, there are proofs which will take say thousands of years to prove on computers, which people have proved on quantum computers. Okay, so that means it's already transcending the usual computing that That's why there is a craze for that. Okay, but what it's going to do, God alone knows. We pray it doesn't. See, everything you do in science and technology is both a boon and a bane. It depends on how it is being used and who is going to use it. The person whether is going to use it or misuse it, God alone knows. Okay, so we only pray for the best. For example, people do all these experiments that people are doing with viruses. Okay, then you could create a mutation that can wipe out like COVID. Thank God COVID just it died down instead of getting more worse. Okay, somehow it died down. Then there's also all these in the Arctics and the caps ice, the glaciers are melting, and then the viruses from which are all inside for billions of years, they're all being exposed. God alone knows how we will be able to tackle them. Okay, if they get into mainstream. So there are a lot of issues. Science is always full of issues. We only know this much and we try to advance, but everything can be used for both good and bad. Every source of power is like that. Everything in nature is like that. So so we only hope that the collective humanity and the people who are in charge of these powers realize what humanity is and have enough sense, avoid things like this terrible war that's going on and that's just destroying a whole nation. Anyway, so
so at what point do people stop waiting for something to be proved and just use it because it's convenient?
Say that again.
At what point do people stop waiting for something to be proved when it hasn't been disproved yet and just start using it because it's more convenient, because it's better, it helps?
No. You see, there are two issues. One thing is that you use something. See, everything when it comes to use, everything is only by experiment. See, when you don't have a theory for it, then people realize that this is the best thing to do, and then it is a matter of several trials and errors. They say that this works up to some degree of accuracy, okay, and then they use it. So that is always there, okay. So for example, I wanted to, usually I'm a very slow lecturer and I want to say a lot of things, and I realize that I have just done 1% of what I want to say, but it's okay. But the point is that you see, there's something called horology, which is the art of timekeeping, okay. So the problem with timekeeping is that this timekeeping has a big history, and see, initially people didn't have any track of time except for the sun's and the moon's movements, okay. Jantar Mantar, where they did all these they were able to keep track of time. Aryabhatta, Bhaskaracharya, etc. Okay, people had some idea of time, okay. But you won't believe it was late, I think something like 13th century, 12th century, 13th century, when decent kind of clocks were invented, okay. And then came the pendulum clock. The pendulum clock was used for about 250 years, okay. When the first version of the pendulum clock was giving a error of 15 minutes per day, okay, and the best pendulum clock, which was used about maybe last century, gave the accuracy was error was 1 second per year, okay, pendulum clock. Then it was replaced by quartz and atomic clocks, okay. So, but even before that, people were looking at the stars. They were looking at the pole star for navigation in the night. Then they were looking at the celestial movements of Jupiter and Saturn and the sun and the moon to get position. So people, of course, we make do with what is available. But the point is that more and more, if you want more and more accuracy, there's no, you need more accuracy and you work towards it. And then there is a breakthrough which gives you that accuracy. But then that breakthrough is, you will see, invariably connected with a lot of math. Okay. So, but I don't know whether this answers your question.
No, sir. My only question was when any property has been tested to a remarkable degree of accuracy, why don't people just accept it? Why do we keep waiting for a proof?
No, that's because you need, see, it's the question of how much accuracy you need. If that much accuracy is good enough, you're happy with it. But there are applications when you need more accuracy. Okay. So, for example, you take lunar landing, lunar missions. Then you want to, there is something called a gyroscope, which tells you the exact position in space. Okay. Now, this gyroscope is a mechanical instrument, at least the older ones. And the mechanical instrument has a least count. You see, every mechanical instrument, has a least count. There is a smallest observation it can make. Any observation lesser than that it cannot make. That is the degree of error, minimum error. So the point is that if you want, suppose I am estimating trajectory from say 1,000,000 miles away. Okay, small, a change in the axis of the gyroscope will take me from the moon and away from the orbit of the moon into something else. Okay. So it all depends on how much accuracy you want. The point is that people want more and more accuracy, and it's the need for accuracy that is driving all this. Now, using your cell phone or tablet or iPad, I can place you within a meter of where you really physically are, and if it is a military satellite, I can place you within a centimeter. Okay, which is what people use to accurately pinpoint and hit terrorists from nowhere. Okay. A person can be, so see, accuracy has its, where it is needed, and then there is a push for that. So accuracy is needed in everything. So if you are in an application that does not need so much of accuracy, you can stop if it's comfortable enough. But that doesn't mean that there could be other applications where you really need that accuracy. And then the more accuracy you need, then you need better systems, and then you need the math, you need everything. So you see, that's how it goes. The more accurate things become, they are needed. Okay. For example, microscopes, right? So microscopes you want to see at cellular level, you want to see at molecular level, you want to see at subatomic level, tunneling microscopes. You say you just don't stop because you want to see. People would like to see what's inside a proton, but they can't. Okay. So I don't know whether this answers your question. The thirst for accuracy is dependent on the need for accuracy.
But even
and
in
there are
something-
always applications.
But even in something as abstract as a mathematical proof,
Pardon me?
but we look for such accuracy even in something as abstract as a mathematical proof.
What do you mean?
Well,
A proof means proof is the very embodiment of accuracy.
yeah, but like
If it's not accurate, it's not a proof.
for the even numbers are a sum of two prime numbers, right?
Yeah.
We've tested for really far, and we
Yeah.
haven't found anything yet, right? So
Yeah.
at what point do we accept that as?
No, we don't.
We just simply won't as long as we don't have a proof written down.
Exactly.
So we're not going to use it to prove other things, even if it's more convenient.
No, you cannot. It's how can you use something which you don't know to be as true in a part of a logical argument? The idea of logical argument is that every statement you make in a logical argument must be deductible as true from the axioms and what is given. So so the point is, in any logical argument, at any place if you bring in something, that should be a true statement. Which means it must have been deduced. It must have a proof. Otherwise, you cannot bring it.
So axioms do have proof.
Pardon me?
All axioms do have proof then.
All axioms?
Do have proof then.
No. Again, I told you, axioms are certain statements which you don't ask for proof.
Yes,
You
so
start with that.
At what point do we accept something that has been tested over and over again as an axiom then?
No. Again, you see, you are making a mistake. See, axiom is something very fundamental. Okay.
Doesn't your
Are
basis
you
of
trying to say
fundamental
that you
evolve
want to
over
take
time?
Goldbach conjecture as an axiom?
Over time, if we were to keep testing it and we didn't find a case that was disproved, wouldn't it count as something fundamental then? Eventually, doesn't our
No. Don't make speculations about what is not. See, in future anything can happen. I can't base my present on what may or may not happen in the future.
Okay.
Please understand. See, the logic is that axioms should be as simple as possible. And from that you have to build everything. Okay. And a statement such as the Goldbach conjecture is not an axiom. I mean, it's a statement. It's a statement about the system of numbers. You know prime numbers, you know even numbers, and then it's a statement that something is happening. That has to be. You have to really prove it. And as far as mathematicians are concerned, since unless you prove it, you cannot use that for anything else. So it's so deep that there is something called Riemann hypothesis. It's called the Riemann zeta hypothesis. This the great mathematician Hilbert, it is said that he said that if he were to fall asleep for 500 years or 1000 years, after he wakes up, the first question he will ask is, has the Riemann hypothesis been proved or not? Okay. Why it's so important is because if you prove it, from that you can get Goldbach conjecture, you can get twin prime conjecture, you can get you can get thousands of theorems as a corollary to that. So you see, there are certain fundamental questions so it's a very deep question. And see, the rule of mathematics is that you don't take something for granted unless it's proved. That is the rule of mathematics.
That's just massively inconvenient, right?
No, it's not inconvenient. I mean, it's a question of truth. It's a question of truth. When you build a higher truth, it should be based on lower, a higher truth. By higher, I mean more complicated truth. It should be based on a foundation which is also built on truth. It cannot be based on a foundation of falsehood. So the point is that every brick that you put into the foundation of the proof must be a solid brick. It must be a true statement, which means it must have a proof. It must be deducible from the axioms and the hypothesis. Otherwise, it's not at all mathematical. Okay. So, but of course, there is a point. There is a positive point to what you are saying. For example, if you take physics, for example, in physics we have what is called as, now people are using standard model, okay, to explain subatomic particles. Then